Hello, everyone. Thanks for coming. I'm Alex Frelas, and I'm joined by my colleague here, Jack Butler, and we're presenting on COVID-19 tracing apps, the proliferation of rush development. Now, a little bit about ourselves. I'm currently a director at a Fortune 500 company, directing a penetration testing team. I'd like to consider myself technical as well as managerial. Some of my interests lie in web application testing, aviation testing, and just enjoying the outdoors.
And my name is John Butler. I'm a mobile application security specialist, and I have a strong background in the prevention of reverse engineering of mobile applications. I currently work as a security specialist for a leading firm in the mobile application security space named GuardSquare, and much of the research and the takeaways that we're presenting on here today were conducted alongside my peers and as part of my daily duties at GuardSquare. Now, to get things kicked off, we're going to provide a brief overview of what we hope to accomplish during today's conversation and to give you a bit more context regarding the analysis we performed and the findings we made as a result. To do this, I would like to give you a little bit more of a backdrop, starting with the purpose of today's conversation, which is COVID-19 contact tracing applications. Now, for anybody unfamiliar with what a contact tracing application does or what the purpose of a contact tracing app is, it's very simple. A contact tracing application is simply designed in order to trace individuals using the application and alert individuals of potential exposures to COVID-19 virus. So if I come in the proximity of another user who is tested positive for COVID-19, I will then receive a notification so that I can go get tested myself as well. Now, as part of today's conversation, we're going to provide a clear timeline of events so that you can understand not only the analysis that we performed, but also the time in which we performed that analysis. We're also going to be discussing the importance of trust, especially as it relates to contact tracing applications and effectively fighting the pandemic. And we're going to be going over our analysis, so our testing approach and our methodology, the body of applications and scope, as well as our findings that were derived from analyzing all of the data that we found. And lastly, we are going to be providing recommendations as well as key takeaways when it comes to any contact tracing application, not just that of COVID-19, but potentially future contact tracing applications as well, and other rushed development scenarios which might equally apply. So now that we've provided a general overview of what we'll be discussing today, we can move on to providing an overview of both our testing approach and our methodology. And in order to do that, I would like to cover these three main points regarding our testing approach. So that's going to be the body of applications that actually were in the scope of our analysis. It's also going to cover the individual controls that we were looking for inside of each of the applications that we analyzed. And finally, it's going to cover a summary of findings based on the analysis that was actually performed. Now, in order to give you better line of sight into not only the analysis that we performed, but when we performed that analysis, I created a slide here in order to provide a general timeline. So you can see in June of 2020, I had the opportunity of analyzing 14 of the original Android COVID-19 contact tracing applications. At the time, the data was limited to Android. These were only APKs, and so I could not evaluate and investigate the iOS side of the house. But at that time, the privacy and security concerns were certainly enough in order to spark an interest in performing a second round of investigation in order to expand that data set perhaps, and also take a look at how new applications have progressed over time. And so that's exactly what we did. In December of 2020, as you can see, not only did we reanalyze the original 14 Android COVID-19 contact tracing applications that we looked at initially, but we expanded that data set by adding another 38 unique Android COVID-19 contact tracing applications, totaling 52 Android applications on the Android side of the house. And we also extended that data set by adding 43 unique iOS COVID-19 contact tracing applications in order to get a better look at what we actually see on the iOS front as well. So in order to provide a 30,000 foot view in a breakdown, you can see that we analyzed 95 applications in total. The majority of these were created by public health authorities around the world. Something that's interesting is that not all of these applications were created by individual countries, but you can actually see that some of these were produced by states and US territories, of which we had the opportunity to analyze some of these as well. Now, I would also like to introduce what's called the Exposure Notifications API. The Exposure Notifications API was created by Apple and by Google back in May of 2020, and the main goal here was to unify the way in which developers create both safe and secure contact tracing applications. And it is quite simple. It works on a very simple but secure Bluetooth implementation. So if I am using the application and I come in contact with another user who has tested positive, I will be alerted of that potential exposure so that I myself can go ahead and get tested myself. Now, once again, this does not rely on any form of GPS tracking information, and it also does not request any other forms of potentially sensitive user data, such as a passport number or a phone number or other pieces of information, which simply aren't required to anonymously, safely, and securely notify users of potential exposures to the virus. Now, I've also provided some developer documentation here for anybody that's interested in taking a closer look. Regarding the implementation and the API itself, you can also see that it provided some links below in order to give you more information surrounding the API, but that won't be the main portion of today's conversation. You know, there were two primary goals when creating the Exposure Notification API, that being safety, privacy, and of course security as a whole. So safely and securely notify users of potential exposures. Goes about this by using Bluetooth and not GPS data, but also to limit the amount of information that's actually collected so that it is not left unsecured and unencrypted for attackers to find later. And so the way it does this is by actually not collecting any additional pieces of information at all, and therefore it doesn't need to be secured. Now, the real key thing to understand about the Exposure Notification API that differentiates it from other solutions or other options is that the first, it doesn't rely on GPS data, which is a privacy concern in of itself. The second thing is that it also does not request any additional pieces of user information, which would otherwise need to be secured. But in some of our analysis, we noticed there were applications that are using GPS data, collecting other pieces of information and not securing that. So with this in mind, there were certainly many expectations and many outcomes of receiving this key innovation, and so that brings us to the next slide. One of the things that we want to do is really discuss some of the key expectations that prompted the creation of the Exposure Notification API. As mentioned, the API's primary goal was to provide core functionality for developers who wanted, in public health authorities who wanted to create secure contact tracing applications. And as part of this, the goal was that if Google and Apple thought that if developers create safe and secure applications, then people are bound to trust those applications. And as a result, they'll use them. Whereas, in contrary, if users do not trust the application, then they're not going to use it. And if the masses of people choose not to use COVID-19 contact tracing apps because they don't trust it, then it's not going to be a very effective utility in fighting the pandemic. So it's very important that people trust them. And in order for people to trust them, they need to be built both safely and securely with privacy in mind. So Apple and Google came together. They produced this API to do just that. And naturally, as part of this, the expectation was that health authorities around the world would adopt this very convenient tool in order to do just that. Now, the results themselves were something different, and this is something that we'll take a look at here. As you can see in our analysis, what we found is that 60% of the applications overall adopted the Exposure Notification API, so 62% on the Android side of the house and 58% on the iOS side of the house. However, 40% of applications did not elect to use the Exposure Notification API, and as a result, they took a do-it-yourself approach to security by instead doing it themselves. So, for example, we noticed applications that were using GPS data, collecting other pieces of information. These tie into some of the security and privacy concerns that we'll discuss later, and some of the unnecessary pieces of data that they collect and fail to secure properly. Now, something that's very important to understand about all of the information and all of the data that we're going to discuss today is that we're not focusing on the 60% of applications which did in fact use the exposure notification API and therefore do have good security posture. We're focusing on the 40%, and that's really where we're going to zoom in order to take a closer look at the 40% of applications which deliberately elected to not use the exposure notification API, and in many cases actually collect additional pieces of information which in many cases were also not secured. So this is going to be our main focus today, the 40% of apps that did not use the exposure notification API. Now, finally, we would like to introduce the individual controls studied. So for each of the applications inside of the body, or each of the applications inside of the scope that we were looking at, so the 40% of applications that did not use the exposure notification API, but instead took a do-it-yourself approach to security, these were the individual security mechanisms that we were looking for. Now, as opposed to reading them all off, I'll let all of the viewers here take a look at these individual controls. But each of these are aimed at removing context from a binary and making it harder for reverse engineers to understand how the application works and therefore how to exploit it. So now that we've explained our testing approach and our methodology, we're going to go into a full overview of the data and the analysis that we actually performed, as well as the takeaways that we were able to derive from analyzing that data. So hopping directly into the data, you can actually see here on our first slide, we are taking a look at the Android applications. Now, of all of the 40% of applications that fell into the category which did not use the exposure notification API, we did take a look at 20 do-it-yourself Android applications. And of them, we have actually mapped the different percentage of those applications that adhered to the controls that we were looking for and possessed these different protection mechanisms. And it's very clear that on the Android side of the house, most applications don't possess these protections and therefore additionally possess weak security posture. Piggybacking off the last slide, you can see on this slide that we've provided a number of applications and a percentage of applications which adhere to the control mechanisms that we took a look at on the previous slide. So, for example, you can actually see that 95% of these applications possess 2 or fewer of the protections that we were looking at. Now, please do bear in mind that the slide that we're reviewing right now is just the Android portion of the applications that we looked at, but just from a 30,000-foot view of the 40% of applications that we analyzed which did not use the exposure notification API, 95% of those applications used 2 or fewer protections, meaning they're not building these applications with security or privacy in mind, and actually 0 of them had 5 or more of these protections. So now taking a look at the iOS side of the house, you can see that we have equivalently provided the same control mechanisms that we looked at for the Android side. And in the top right-hand corner, you're going to see that for the iOS side of the house, we actually analyzed 18 do-it-yourself iOS applications. By do-it-yourself, we mean these applications deliberately elected not to use the exposure notification API and instead elected to implement controls themselves. Now, what you can see is that most of these features are actually implemented very conservatively across the applications that we analyzed, and actually app attestation and name obfuscation just simply don't appear at all. So once again, on the iOS side of the house, we are very quickly realizing that robust security does not seem to exist inside of the majority of these contact tracing applications. And now, once again, you can see that we have provided the same chart that we did for Android in order to display the number of applications and the percentage of applications which actually adhered to a certain number of the controls that we were looking for. So in this case, we can actually see that 61% of the iOS applications that we looked at, so 11 of the 18, actually possessed 2 or fewer controls, and in general, 94% of these applications possessed 2 or less. So on the Android side, we can see that 95% of those applications, and on the iOS side, we can see that 94% of those applications possess 2 or fewer of the controls that we were looking for. Once again, representing that these COVID app contact tracing applications are not being built with security in mind. Now, beyond the lack of security controls, which we were able to highlight in previous slides, we also believe that privacy concerns should be a large portion of today's conversation and should be illuminated. So we're going to take a look at GPS privacy concerns, which we observed in a number of these different contact tracing applications. And we're going to start by calling out the fact that many GPS apps, or a number of the GPS apps that we observed, actually collect additional user information which is not necessary, such as a passport number, phone number, a device ID, or other pieces of valuable information which aren't required to anonymously notify users of potential exposure. Additionally, those sensitive pieces of information were in some cases stored insecurely, such as in unencrypted SQLite databases, or potentially leaked in other ways, making them effectively unencrypted rather. So it's very safe to say that this is definitely a privacy concern. These applications actually don't need to collect additional information, which is the point of the exposure notification API, which only relies on Bluetooth and does not collect any other sensitive pieces of user information. And with that being said, this can actually call into question the safety of these applications and potentially hinder the value of contact tracing applications when it comes to combating the pandemic itself. So now we would like to summarize the results. And on the bright side, starting with the good news, 60% of applications did indeed adopt the exposure notification API. And that's really good news. But what we really focused on during this conversation was the 40% of applications that in some negligent way elected not to implement the exposure notification API, and in many other examples actually performed other pieces of unnecessary and unsafe forms of data collection like GPS tracking information, passport numbers, phone numbers, and more. On top of this, we noticed that many applications, again, were leaking that information through unencrypted SQLite databases, HTTP cache, so on and so forth, and this is a big concern. So that brings us to our second point. Reliance on GPS tracking data, I think, has been proven to be an inferior method than Bluetooth. When it comes to contact tracing applications, these need to be built with privacy in mind, and Bluetooth does a great job. It gives you all the tools that you need to both detect when you're in the proximity of somebody who has been exposed to COVID, and therefore alert you to the fact that you yourself should go get tested as well. So don't use GPS tracking data, use Bluetooth, use a common API like the exposure notification API. And again, don't collect other unnecessary pieces of data which just very simply aren't needed in order to notify individuals of exposures. And finally, in summarizing results, I think it was very clear based on the previous slides that there was a gross lack of static and dynamic protection when it comes to the applications that we really dug into and took a look at all these individual security controls. What we found is that due to these the lack of obfuscation, the lack of encryption, and the lack of runtime protections that were embedded inside of these applications, it would be very easy for reverse engineers to tamper with and change and exploit these applications in different nefarious ways.
Some other observations that we made throughout our testing and research was, first of all, that application security is not determined by a nation's wealth. So for example, if we look at Israel, who's number 32 out of 196 in terms of GDP in the year 2020, they had significantly worse application security than some of the countries in Africa who had their own contact tracing app. Now that's contrary to what we thought. We thought that a country who had high GDP had a lot of money for developing a contact tracing app securely, but that's not the case. Second of all, GDPR and HIPAA violations were noticed, especially in the DIY apps. England's was one. Their test and trace program broke GDPR data laws because they weren't adhering um, to GDPR regulations as it pertained to the storage and processing of data. Now, thirdly, there's the encouragement of waiving data privacy rights. There are users who are downloading these applications thinking that they're robust with security and privacy in mind, but that's not the case. So there needs to be transparency, and there wasn't in terms of how privacy was being handled. Let's move on to flawed development and integration. We clearly noticed that development teams were having difficulties in a variety of areas. First of them being timeline sensitivity. With the pandemic picking up in pace, development had to be rushed to get a working application out as soon as possible. The sprints, as a result, were focused on fixing functionality or creating that functionality, leaving little consideration for security in that time. The second thing we noticed was that the development team had to choose between, their approach to constraints, whether they wanted quality, which would require a long development time, or if they wanted a short release time, but as a result, control the spread and potentially save human lives. The third difficulty that we saw these development teams have was the fact that this was such a unique solution. There hadn't been a contact tracing app before that had to be released on such a large scale. There was no previous poster child. I don't think that a developer could go onto Stack Overflow and get the necessary code and call it a day. So that wasn't really possible there. And the fact that these applications were handling sensitive data, this had to be looked at in terms of privacy. Some applications, of course, considered privacy and security very well, others didn't. But either way, there had to be some sort of consideration for that sensitive data even at minimum. The rushed development of these contact tracing applications didn't come without any effects. There's actually quite a few effects that came about as a result. As I mentioned in the last slide, there was a main focus on functionality of the applications and a limited regard for security and privacy as a result, just mainly because the goal was to develop an application as soon as possible and release it to the public. Furthermore, there was a lacking of features that would allow for integration with other apps or COVID apps. Let's say the European Union wanted all of Europe's countries to integrate into one application. This wouldn't be possible because this integration feature wasn't built in. However, as a result, less time was spent on development, which means that getting to the controlling of the spread happened sooner. So you can claim that as a benefit. Lastly, there's an ethical dilemma. These developers know that there's a known risk of security in these applications, yet they're still releasing it. Well, the question is, do you release an app that is unhardened due to lack of time and money? On one hand, the spread might be thwarted, but at the same time, it's opening doors for a long-term headache if these people's data gets stolen. And you have to weigh the long-term effects against the short term in that case. Let's move on to recommendations for time-boxed development. So the first recommendation is to unify apps, and that can be done in one of two ways, or both. The first being using a common API, and the second being consolidating apps. So the first way is, using one of Google's or Apple's APIs, also known as the Notification Exposure API, or similar. Now I put an asterisk there because I believe that it doesn't necessarily have to be a private company's solution. It could be a public government created solution. But either way, global issues should be fought on a global scale. There should be that common API that should be utilized when it's there. The second, as I'd mentioned, is consolidating apps. There's way too many apps on the app stores. Users have trouble knowing which one's legitimate, which one's not, and the fact that there's so many state level apps, that's just contributing to the issue. And to that, we're just saying no. Let's skip not having these state level apps. Country is fine, but making sure that it's utilizing the common API and not a do-it-yourself one. Anybody who's not complying with this, our thoughts are that they should be fined. There's going to be proposed contact tracing app requirements, and anybody who's not adhering to them should be fined. The second thing we'd like to recommend is a security-focused SDLC. Now, for those of you who aren't familiar with what an SDLC is, it's a software development lifecycle, and it's typically found in companies and pertains to how development goes from start to finish. We're particularly recommending a shift left approach, which means including security earlier and at every phase, meaning that it's everywhere, and that it's a forethought, not an afterthought. We're recommending that teams aren't siloed, so if there's a security team, we want them to work with a development team and for communication to be facilitated. There doesn't have to be a pick one approach to choosing either functionality or security. You can have both, and that's the fact that these development and security teams can work in parallel together, especially when new features are being released. There could be an iterative approach where security is constantly being checked in these features. One thing that would allow for security tests in these types of feature releases is something called a technical security review, which documents that there's been scanning in the code that's been performed, documents the inter-service communication. Let's say the service has to communicate with another service, that will be documented there, along with any scanning results or testing that had been done. If there is no software development life cycle, in the case that a company doesn't have to adhere to, let's say, PCI regulations or HIPAA, what have you, then typically you can hook it into an existing change management process. You can hook security processes into that because whenever there's an application that gets added to an inventory, let's say, typically there's a change management process for that. And very similarly, you can just include security aspects to be included in that.
Now we would like to go over some development recommendations for current and for future contact tracing applications alike, starting with use a common API. If tech giants like Google and Apple are going to give you all the tools that you need to succeed in creating a contact tracing application built with both security and privacy in mind, use it, implement it, and benefit from it. Not only are you going to benefit from it, but your users are going to benefit from it. They're going to know that as a result that their information is safe, that they don't have to worry about that information being leaked due to negligence when it comes to security. And as a result of being able to trust the fact that those applications are indeed built with both security and privacy in mind, they're more likely to use those applications, which is going to make them a much more effective utility in fighting a pandemic like the one we've gone through or any other potential future pandemic in the future. As part of this, don't collect or store any other pieces of user information which are not required to alert users of potential exposures. So again, going back to the exposure notification API, collect and use as little as possible. Don't collect GPS tracking information. Don't collect other pieces of user information. Again, try to use something like Bluetooth. Don't collect other pieces of information. One of the key benefits to not collecting other pieces of information is, of course, then there is no risk of that information being leaked, and therefore you don't need to secure it at all. The second recommendation that we have is to adhere to security standard or framework like OAuth's Mobile Application Security Verification Standard, which, as it sounds, acts as a blueprint for security architects or mobile developers alike who are looking to build applications with both security and privacy in mind. And we would also recommend that if for any reason you do, or public health authorities do decide to build contact tracing applications, they do not decide to adopt the common tools that are given to them, like the exposure notification API and future use cases, to actually utilize code hardening solutions if needed. So if you do decide to collect additional pieces of user data of any kind, then it becomes your obligation and your liability to secure that information. Otherwise, if it does get leaked, it's your fault. So ultimately, what we've found is that while many teams do have what it takes to build perfectly functional applications, baking in security is something completely different. And especially on such a rushed timeline, this can be a very large task. So for that, there are code hardening solutions that will allow you to implement multi-layered protections, both static and dynamic, to provide robust security inside of applications that will ward attackers and make it infeasible to reverse engineer those applications in a very short amount of time. So those would certainly be recommended by us if for any reason public health authorities decide not to adopt a common API and to actually go ahead and collect additional pieces of unnecessary data. And the final product we hope is that more safe, secure, and privacy-focused contact tracing applications. By creating applications with security and privacy in mind, the ultimate goal, as it always was, is that users will trust those applications, they'll use those applications, and by using those applications, we'll all be safer. We can make a difference, we can make an impact, and hopefully find a way to more effectively fight the pandemic. Now with this, we'd like to move on to some general agnostic recommendations for code hardening solutions, just so that we can be most helpful. Again, going back to the main point, a code hardening solution shouldn't be needed when it comes to contact tracing applications. These applications should essentially be shells, which really only alert users of potential exposures based on Bluetooth activity. But if for any reason you stray from that recommendation and you do decide to, again, collect additional pieces of information, it does become your liability, your obligation to secure it. And if you don't have time to do that, you don't have the in-house skill or specialization to do that, then I would have to say that this is very common. And we'll discuss this in following slides as well. In order to make life easier, faster, and more secure for everybody, you can adopt a code hardening solution. And so we're going to run over a couple different code hardening solutions which can help vastly improve the security posture of applications, both statically and dynamically, by applying multi-layered protection in a very short amount of time, so a number of weeks. So starting with DexGuard, DexGuard is an Android hardening solution. Once again, it is a fully encompassing suite of tools which is designed to specifically harden Android applications against both hackers and reverse engineers. It does this by, again, applying multi-layered protection, both static and dynamic. The same is true of IXGuard, which is its iOS counterpart. It's designed to provide an equivalent level of protection, but for iOS applications. And so if you are building an iOS contact tracing application, it does collect additional pieces of sensitive user information. It would be a good idea in order to secure that using a solution like IXGuard. And finally, there's ThreatCast. ThreatCast will provide real-time threat event information so that you can actually monitor what's happening and how that application is being attacked in real time, and then respond to that proactively. Now, finally, we would like to move on to the triple constraint and the importance of actually adopting the triple constraint. Now, the triple constraint is the idea that in any project management scenario, you really have to choose between time, cost, and quality, and oftentimes you can only pick two. Now, in this case, what we found is that many teams did have a very short amount of time to develop applications, and they weren't willing to put money into securing these applications either. As a result, the quality really suffered. What they could have done is they could have put in some more money in order to employ a code hardening solution that actually encrypted and secured all of the additional information that they collected, and this would have been a much more responsible route. The second thing that we would like to cover is resource allocation. What we find is that professionally speaking, most teams certainly do have the in-house specialization needed to create very functional and performant applications. But what they don't have is the in-house specialization needed in order to bake in robust multi-layered security that is truly capable of warding and making it infeasible for very skilled reverse engineers to do just that, reverse engineer and tamper with those applications. So if you happen to fall into the majority of teams like that, then our recommendation is don't try to reinvent the wheel. Utilize a code hardening solution in order to very quickly and conveniently build in security to your application so that you can protect the user base. And ultimately, as part of this, it bleeds right into the rest. Avoid do-it-yourself security implementations like we observed here in this data set. So again, adopt the tools that are given to you, benefit from the tools that are given to you. If tech giants like Google and Apple are going to give you a common API, which is designed to help you build core functionalities into applications in a safe and secure way, certainly use them. But don't expect, high quality, low cost, and low time commitment when it comes to really anything in life.
If you enjoyed the topic of this presentation, we'd like to recommend some ideas for future projects that you can take on yourself. Quite simply, vaccine passport applications. They're very similar to contact tracing applications, but they've had more development time as they're not time pressed in terms of development as they're racing against the surging pandemic. They're also more unified, meaning that a whole region, such as the European Union, is only relying on one application versus a multitude. But there's still a reason to be skeptical because we've seen the way that the development approach has been for the contact tracing applications. Despite there being more time, it doesn't necessarily mean that development has included security practices and processes. Some test cases we'd like to recommend there is seeing if you can change the approval status of uploaded COVID tests, and also seeing if you can bypass the proof of vaccination validation, where I believe you upload a picture of your vaccination card. And with that, we'd like to open it up to any questions. Thank you.